Hi everyone. Uh, Welcome back uh, to another RISE session, RISE Journal Club session. And today we have Kushal Vyas from RISE University, and he will be talking about implicit neural representations for signal representation and segmentation. Uh, Briefly introducing Kaushal, he's a PhD student at Rice, working on novel machine learning methods and data representations for medical and scientific imaging, alongside research in machine learning for large signals. His work includes implicit neural representation of signals, and he was recently awarded the MICCAI Best Paper Award at MICCAI 2025 for developing neural fields that jointly enable signal representation and segmentation. Prior to his PhD, he worked at Samsung Research America on machine learning and computational photography and earned his master's degree from Carnegie Mellon. Kaushal, you can take it.
Thanks, Pulkit. And it's a pleasure to be discussing my work at the MICCAI Rise Journal Club. Um, hi, I'm Kushal. I'm a PhD student at Rice, as Pulkit mentioned, and I'll be talking on implicit neural representations for signal representation and segmentation. And this is going to be mainly two works that are sort of connected. So the first work is going to be Strainer, which we published back in Europe's 2024. And the next work is going to be MetaSeg, which was awarded the Best Paper Prize at MICCAI 25. And I'll explain both of them so you see how everything builds up together and it ties into each other. And firstly, just a big thank you to all my collaborators, my PIs, and my fellow co-authors across different papers. I think none of this work would be possible without them. And then also thanks to our funding sources, because without their funding, none of this work would be possible. Okay, so let's talk about implicit neural representations first as an introduction. So basically, an implicit neural representation, or INRs for short, you can think of them as like a L-layer, multi-layer perceptron. They are reasonably simple models, the input to which is the coordinates of a signal, and the output is the intensity or the pixel values at those coordinates, right? So this is quite different from like convolutional networks or transformers where you expect your input to be the image itself or the signal itself, right? For INRs, the input is a set of coordinates, and the INR maps the coordinates to the signal values, essentially learning some sort of representation in the weights of the signal in the weights of your neural network. And typically you have one INR for like each signal. So it's a signal specific neural data structure of sorts. And because of its design, you have very favorable properties, such as an INR implicitly offers you a lot of compression. So you get a compressed representation of signal in the weights of your multi-layer perceptron, but you still have a high fidelity representation. That means when you render your INR and you reconstruct your signal back, it's really high quality. The other benefit is that since you have a neural network essentially mapping coordinates to a signal, it also has the potential to learn a continuous signal representation. And by that, what I mean is you could just input fractional coordinates to your INR, and you can get interpolated values, right? So interpolating, or you could train your INR on a sparser set of pixels or sparser set of your signal, and you can still get interpolation capabilities. Three, because it's technically a deep network, there's a lot of deep priors which are inherited, and you can use that for which are useful for inverse problems. And the last thing is that INR scale efficiently to larger signals. So, for example, INRs are also known to like scale with signal complexity and not necessarily size, right? So you can have a really like big complicated signal, which would require a larger INR, but you can have like a sufficiently large signal which is not as complex, and you could get away with a smaller INR. Um, and so far, INRs have been used for scene representation primarily and like imaging. So in scene representation, like a few very well-known works are like Siren and Wire, which are basically sinusoidal and wavelet based INRs. There's also neural radiance fields, which basically shows how to use INRs to reconstruct 3D objects from multiple 2D projections. And there's also Instant NGP from by Mueller et al., which scales the entire idea of an INR to gigapixel level signals. And in imaging, the benefit in imaging is that since INRs are single signal models, you don't necessarily need a large data set to train it. It can be more or less used in a self-supervised way. They can be used in like a lot of imaging applications like tomography. There's ultrasound imaging as well. And then you could also combine it with more physics-based machine learning models and like estimate more physical properties or like things like flow in porous media. And so far, INRs, the adoption of INRs is very heavily done for scene representation and imaging. And before we go further, let's just quickly talk on how an INR fits a signal so everyone has the context. So as we said, an INR is just a set of linear layers, typically set of linear layers. The input are the coordinates of the signal, and you expect the output to be the function value at those coordinates, right? And so you train an INR iteratively to like typically overfit the given signal or measurement you have. And you would do so by minimizing this objective willow, where you're trying to find the right parameters that minimize the mean squared error between your ground truth signal, or it could also be your observed signal, or like a corrupted measurement that you have, and against the output of your INR. And typically for inverse problems, you may also use a forward task specific operator, like denoted by A over here. And a quick example of that would be let's say you're doing super resolution, uh, then your quote unquote Y ground truth would be the measured signal which you have, which would be the low resolution. Your F theta of X, which is your output of your INR, would be the latent high resolution image which you want to recover. And A, which is your task specific operator, would be a differentiable downsampler, right? Uh, so this is an INR would eventually iteratively fit a signal, and like what you have is either a latent solution or the signal representation itself. However, like most like deep learning architectures, which get initialized in a principled but random way, INRs are also like initialized in a standard way. But oftentimes, what happens is uh, the convergence, the optimization trajectory of an INR starting from its random initialization to the final image representation that it learns is often very random. And what happens is that you may end up for two similar images. For example, out here I'm showing you two face images. You might end up with the learned INR features which are highly dissimilar. Right? And that poses a challenge in machine learning because if you want to do anything downstream, like a downstream task with these INR features, you sort of require them to have some amount of generalizability or some amount of like consistency over these features, which would allow you to do downstream machine learning tasks. And which is why obtaining generalizable INR features over a distribution of signals is actually a non-trivial problem. Right. And so this makes us ask the natural question that, okay, like, can we borrow some tricks from the original machine learning workflows, which is, can we use data to learn some kind of INR parameters as an initialization, right? And the goal is that we learn a data-driven initialization for these INRs, which would eventually give us more generalizable features for downstream tasks and potentially tasks like segmentation. And yeah, there are a few approaches, such as you could meta learn over a bunch of like face images. You could also use something like a hypernetwork with which you could learn INR parameters more efficiently. But these are also methods which require large amounts of training data, and that might be scarce, especially in scientific and medical imaging. And it's also difficult to scale to high resolution or larger size signals, right? All of these approaches would require to have like a well curated data set and whatnot. But there's a interesting caveat here, right? So we know that natural images exhibit an underlying structure, right? And a very simple example is, for example, you just take face images. So for face images, all faces have like two eyes, one nose, one mouth. It's reasonably similar geometry, right? And the fact that natural images have an underlying structure was previously well studied. Like I think one of the original papers that surfaced this observation was like natural image statistics from Simoncelli and Osselhausen. And then I think Eigenfaces was another seminal work where people like over a data set of faces, like expressed decomposed it into a set of orthogonal bases. And even something as simple as low pass filtering and averaging a bunch of faces will show that there is an emergence of an underlying structure. And so the question is that how can we use that underlying structure to basically, or like, could we encode that underlying structure in these initial INR parameters? And the goal of which is that eventually, because you encoded the structure in the weights of INRs, you sort of have features which are more consistent or more generalizable, right? And are not that dissimilar across multiple face images, as an example. And so with that, I'll first talk about Strainer, which was our first work, which we published in Europe's 24, which is called Learning Transferable Features for Implicit Neural Networks. And basically what Strainer does is it exploits this fact that natural images have underlying structures as long as they are belonging in the same class, and maybe that structure can be encoded in these layers of INRs, or in these initial parameters of an INRs, which can then help you like either fit signals better or represent signals in a more general way, uh, and just maybe help with the convergence of an INR while fitting a signal. So as we go further into what Strainer does, I think it's this is an interesting visualization which I really wanted to show, which is if you look at how an INR fits a signal, it fits layer wise in a coarse to fine fashion. And what I mean by that is we all know that the input to an INR is a set of coordinates. And you can think of this as basically like a plane or a flat piece of paper. And you can think of an INR doing origami at each layer. This is just an analogy, but to help simplify the explanation. And basically, what we notice is each layer progressively, in a nonlinear way, will warp these input coordinates until basically you match the morphology of your actual signal. And what's interesting is that in these initial layers, you see that low dimensional structure emerge, which was similar to uh, how we saw low dimensional structure emerge in natural signals a few slides back. Right? And the point is that can we use those observations to come up with a clever way to capture that low dimensional structure? Right. So a vanilla INR, or like a typical INR, only fits one given signal, right? So the input is coordinates and the output is signal. What we do with Strainer is we actually share these initial layers, right? And by sharing these initial layers, you induce a bottleneck. So you're forcing your INR to actually learn these low-dimensional structural correlations in these initial layers. And then you have these deeper layers which are more specific to each signal. Right, so it's almost like you constrain these initial layers so that you can capture whatever is common. Because and essentially what you're doing is you're jointly fitting all signals during this training time. Right? So by sharing these initial layers and jointly fitting all signals, your the parameters or the weights of these initial layers are forced to capture all low dimensional structure across multiple signals. And then at test time, or when you want to fit a new image, you initialize your INR with these parameters that you learned during your train time, and you just have like a randomly initialized decoder for the signal, and then you just fit everything at once. And I'll go more into the process. So, for example, one second, yeah. So, for example, let's say this is the training phase of Strainer, right? So you have the shared encoder, which is a set of initial layers which are just shared across like some signals which are jointly fit to the INR. And then you have these signal-specific decoders, which are just randomly initialized, basically projection layers that map the encoder features to the signal. Now, during train time, what happens is you minimize a joint, like summed loss of all the signals that are being fed to this entire strainer module. Right? So you can have n signals. And in the strainer paper, we explore with n equal to 10, where we notice that even 10 signals are great to give you a very high quality initialization, like just 10. So you just take like n signals and you're jointly fitting them to the strainer module, and you minimize this loss. Now at test time, all you do is you initialize your encoder with the pre-trained features that you had before. and then you still have a random decoder, and you fit this new signal at test time, and you follow the same optimization where you're optimizing all the parameters, the decoder and the encoder parameters. So it's almost like you're fine-tuning your model at this point. Right? And but now what you have is a data-driven way to learn the initial parameters of an INR, right? And this configuration of strainer specifically is very interesting because you don't need more sophisticated methods like using a transformer hypernetwork or meta learning, these kind of things, right? It's very easy to just like share a bunch of layers and have signal specific decoders, and this is inherently also very scalable. And we then were curious as how does our initialization perform when you actually fit a test set. So we evaluated on syllabi high quality, which are face images, um, on like 178 by 178, because we had to be consistent with all baselines. And as you can see that a siren INR over 2000 iterations would get like a PSNR of somewhere between 40 and 50. And more sophisticated methods like trans-INR, which is a transformer hypernetwork, for learning the initialization of INRs would get something around like 50 plus. And then Strainer, which is only trained on 10 images from the Celeb HQ dataset, gets a staggering PSNR of almost 60, right? And this shows the effectiveness of one, how lightweight our method is to learn initialization, but it also suggests that by sharing these initial layers, you actually capture very structurally relevant features uh, for implicit neural representations, right? And these features are essentially serving as really powerful, quote unquote, transferable features, like transferable initializations, which work well at test time. And just to show how lightweight it is to train Strainer, like Strainer with like trained on 10 images would would be like 200,000 parameters, and it takes almost like 24 seconds on an NVIDIA A100. For example, like other methods like using a transformer would require a lot more parameters, a lot more time to train. It requires a lot more engineering to be done for it to converge. Right? And I think what's interesting is that it's sure strainer features are high quality initialization for INRs, and you can fit signals faster and better with it at better quality. But it's interesting to see how with each iteration the quality changes. So out here we basically show like the optimization progression of strainer and siren. Siren is the baseline implicit neural representation here. So they both start off with similar like PSNRs of like 8 dB. But with strainer, you already see some kind of a structure in like right at iteration zero. And as you go more with like as you go at like by 50, 100, and 2000 iterations, you observe that the quality of reconstruction achieved by Strainer is really, really high, right? And I think by iteration 100, Strainer is already like 8 dB better than Siren, which is quite a good jump. And by 2000 iterations is almost like more than 15 dB better than Siren. So by leveraging like a small set of training data, you could learn very high quality features for INRs, which you can later use to just make more powerful INRs. And what's interesting is we wanted to look at what's encoded in these shared layers. So if you take the last layer out of the shared encoder and you run a PCA on these encoder features, you'd find that strainer encodes the structure of, like, for example, if you're fitting a cat, strainer encodes the structure of this cat face very, very clearly, right, in the PCA space. And on unlike Siren, where you see that iteration zero is still pretty random, like you have random components. Iteration 50, you sort of see like the cat face emerge, but like if you compare it with Strainer, the high frequency details in Strainer are much, much more apparent, and even at iteration 100. And then what's more interesting there is if you visualize the Fourier transform of these of the reconstructions at those iterations, you'll observe that like Strainer has high frequency coverage right from like iteration zero, but iteration 50 and 100 also show sufficient high frequency coverage. And then for Siren, you see that the as you learn, the high frequency coverage is increasing with time. Maybe not as much as Strainer. And it's what was something interesting that we found is while While Strainer does well on in-domain images, we found it very interesting that if you train Strainer on something like faces, or flowers or Stanford cars, as shown here, it will perform really well on an out-of-domain example, which is, for example, MRI scans, right? And this is interesting because it means that trainer is capturing something about natural images, or maybe the frequencies in these natural images, which is helping it generalize to these out-of-domain signals, right? And this is an interesting point that 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 would warrant more exploration. Um, and I think it's also interesting to see that other methods as well uh, sort of perform well with out-of-domain generalization. So basically, like INRs fit to one signal can oftentimes serve as a good initialization for other signals. And what would be the takeaways from Strainer? Like one, basically INRs learn highly transferable features, much due to their course to find signal fitting. So these initial layers which encode these low-dimensional structural features, you could use them to initialize a new INR to fit similar signals, right? Like how we saw with Strainer. Second, sharing of these initial layers as a bottleneck definitely helps you learn more meaningful features common to all signals. And then Strainer paves the way for learning potentially cross-task correlations across signals as well. And this is something I will now build upon more. So what do you mean by cross task, right? So, for example, image segmentation is a great example of maybe Strainer or some INR trying to learn cross task features. And what I mean by that is it's very intuitive. Like when an INR fits a signal, I think asking the question that, hey, does it also know uh, like which class does each pixel belong to, right? AKA segmentation. Is that a reasonable question? And for that, I think that's a reasonable question because an image and its segmentation mask, they both share a lot of common structure, right? So we recently saw in Strainer that yeah, these initial layers can be useful for encoding this low dimensional structure, which is common across signals. And it turns out that for image translation tasks, like one of which being segmentation, that also holds true, right? And then the question we ask is, can an INR just fit to the signals be used for computing its underlying segmentation map? Right. And so with that, I'll now talk about MetaSeg or fit pixels get labels, meta-learned implicit networks for image segmentation. So this was the work we presented at MICCAI 2025, and we won best paper for it. So basically, before I go into the hypothesis, like so far, the way segmentation has been done in the medical community, it generally uses like a CNN or a CNN and a transformer or a VIT, and basically like the image is an input, right? And out here what we are proposing is a different way to like do medical image segmentation where you're using an implicit neural representation. So your inputs are essentially coordinates, and now you have like the metaseg architecture where you have these initial shared layers, uh, and one reconstruction head which reconstructs the signal, which fits the signal, and the segmentation head which decodes these learned INR features into per pixel segmentations, right? So you have one head to fit the signal, one to like get the labels. And you have these initial shared layers, much like Strainer, to basically capture features which are highly common and correlated across the signal and the segmentation. And also because these initial layers will encode like the same sort of low dimensional structure between the signal and segmentation. Right. And to fit the signal, we typically use L2 or reconstruction loss. And to fit the segmentation, we would use the classification loss, which would basically be like softmax probabilities on these INR like features for each pixel. Right. And what we now do is we want to learn an initialization which is not only promoting high quality image fitting, but also allows you to encode semantic features in the shared layers or in the bottleneck. And for that we use MAML, or like we use a popular meta learning method, which would allow us to jointly learn an initialization between signal fitting and segmentation. And the way MAML works is you basically fit an INR on a random pair of image and segmentation maps for T steps, right? And for your T can be thought of like the number of steps you want your INRs to like fit your signal in. And once you fit it for T steps, you apply the gradients to your initial parameters and you move your gradients in the direction of your converged parameters. Now you Now you assume that as the new initialization for INRs, and then you fit another pair of image and segmentation map. And then you again move the parameters in the direction of your converged parameters. And you keep doing this over and over again over a large data set of image and segmentation maps. So we use the OSS MRI data set in our case. And you basically end up with an initialization which will like not only allow you to fit signals really fast, but you have some kind of semantic notion encoded in them at the same time. Now, once you've used meta learning to compute your initialization, you still have to refine the segmentation head, and this is one important step in MetaSeg. So the initialization only allows you to fit signals better, or maybe fit signals better in a more semantic way. But you eventually have to decode every feature vector for each pixel into a pixel-wise segmentation one hot vector. Right. And for that, we fine tune the segmentation head by basically creating a data set of these per pixel INR features while fitting each signal. And then we use the classification loss, and then, like, for example, a focal loss, which is a weighted cross entropy loss for segmentation. And you apply the loss between the one hot like pixel labels and the INR feature vectors. So essentially, you're training your segmentation head or fine tuning your segmentation head to perform per pixel segmentation. And once that is done, you freeze your segmentation head, but you still treat the image INR the way it is, and then you just iteratively start fitting signals. And you notice that as you iteratively fit the signals, the segmentation map also starts evolving. And then let's say we decide at training time that t is equal to 100. We you'll not only get like a high quality signal like high quality signal representation, but you also get a high quality like segmentation. And out here, you notice that the dice is 0.95, showing that it's a really high quality segmentation. Note that in this step, the gradients only flow to the INR, which is reconstructing the image, the actual MRI signal, but no gradients are flowing over the segmentation head. So the segmentation head only decodes pixel-wise features into the segmentation labels. So for more experiments and results in MetaSeg, we basically experimented with 2D and 3D MRI segmentation. For 2D MRI segmentation, we use 5 and 24 classes OS's MRI scans. We did a train split of 214 images for train, 100 for validation, and 100 for testing. And we pre-processed these images to 192 by 192 resolution. For 3D MRI segmentation, we just did 5 class segmentation, and we had the same train test split, and we pre-processed it to 80 by 80 by 100 spatial resolution. And what we noticed, we also compared it with like popular unit baselines. Like for example, we compared it with the MRI segmentation PyTorch unit model, which exists as a popular baseline, and we noticed that a unit, which is a convolutional model, would get a dice of 0.96, but MetaSeg also gets a dice of 0.93, which is very impressive, uh, given that it's an INR which is only fitting a signal. And for 24 classes, we observe that a unit gets 0.84, whereas a metaseg is getting a dice of 0.86. And for 3D MRI segmentation, we compare with SegResNet, which is a residual unit for segmentation, NISF, which is another popular INR baseline for 3D segmentation, and Metaseg. And we notice that Metaseg gets a dice of 0.91. And while we get impressive die scores, almost comparable to a unit, we are at least 90% more parameter efficient, right? And that's like units are generally convolutional models, and based on the skiff connections and architecture, you might end up with a high number of parameters. But INRs are just like MLPs, and they have reasonably like fewer parameters. And I think that is very impressive. And then we also want to look more into how does MetaSeg generalize to large and small structures? For example, here are two different brain scans from two different people, and we observe that MetaSeg is able to handle like high variations in structure. For example, the gray matter and the brainstem across both these different examples are highly varying. Like gray matter is like something which is extremely like uh, nuanced and irregular across different examples. So, but MetaSeg is able to capture that well. Brainstem, for example, out here can vary from a large volume to like an extremely small region. That works well as well. And then also like more delicate and deeper brain features like the ventricles and hippocampus, which are also extremely important from a diagnostic point of view. It's able to accommodate them quite well. And then what's also interesting is that because INRs can inherently be scaled to very easily to 2D and 3D scans or like higher dimensions. We just fit a 3D brain MRI scan to MetaSeg, and it is able to like learn the 3D segmentation quite well. And here you notice that we fit this 3D scan. We not only get like 3D segmentation, but you can because INR, you can query at arbitrary coordinate locations. You can query the INR at different viewing planes and get consistent 3D segmentation as well. And out here you see that across the different cross sections, you still retain a die score of zero point 0.9 and higher, which is very impressive. And this is useful because especially while doing brain surgery or like when you want to view your entire volume from a completely different viewing plane, an INR will allow you to do that. You can slice at arbitrary plane locations. And then lastly, what's interesting is we wanted to see how if MetaSeg's encoder actually captures any semantic features. And for that, what we notice is like we take the PCA of these shared encoders and we observe that for a standard INR, which has seemingly random components encoded in its latent space, MetaSeg has different regions of the brain being very correctly encoded. And for example, here you see a lot of like the gray matter being encoded. Out here you see ventricles clearly visible. So it's interesting that doing this meta-learned initialization, you end up with a lot of semantically aware internal features of your INR. And then the takeaways of is MetaSeg is basically a novel framework that uses implicit neural representations to fit signals. And by fitting signals, you can also later decode each pixel into a per pixel segmentation map simultaneously. Uh, we also observe that MetaSeg performs comparatively to a lot of baseline units with 90% fewer parameters. So that's great for low resource setting. So you could train this and maybe have it running on a smaller GPU at test time. And we propose that by using this novel meta-learned initialization scheme, where you can encode signal intensities and its semantics inside an INR, it enables you to do 2D and 3D segmentation in a completely new way, which previously was always done by CNNs or transformers and models like that. So in summary, we have like sharing these initial INR layers helps to learn meaningful cross signal and also cross task feature correlations. So in Strainer, we saw that you can have multiple signals and you can fit like multiple signals having similar structures. So you can have cross signal correlations. And in MetaSeg, you saw that you can have like the signal and the segmentation map. So you're learning cross task feature correlations. And then these features, like the way Strainer and MetaSeg are set up, like sharing these initial layers will often help you learn these features which are more generalizable. And lastly, I think compared to units and transformers, which are very powerful models to do medical image segmentation, I think MetaSeg is offering a new, fresh alternative to look at how we perform medical image segmentation today. And lastly, this is a quick um, quick slide on a PyTorch. So we developed this PyTorch library called Alpine, which we use for pretty much all of our INR projects. And I just wanted to put it out there for the community because if anyone's using INR in medical imaging, Alpine is a great tool to use. Uh, it's very easy. It's almost like adopts the scikit-learn kind of flavor where you can fit and predict signals. And maybe this is something anyone wants to try out in the community. And thank you so much. I can take questions now. And these are the links to the papers and the QR codes to if you just want to scan and open it on your phones. Oh, there's a question. So there's a question in the Q&A panel. Beyond computational efficiency, what does this represent? For example, in medical domain, not only VSNR, but physical anatomy is more important. Do you have insights into what trainer features are learning? So that's a great question. So in the strainer paper, there's a figure 6, which is what I would refer. I don't have it as my backup slides, but in figure 6, we actually show how strainer features encode more low dimensional structures. Not only low dimensional structures in your initial layers, but also the deeper layers learn more signal specific features. And compared to other methods like meta learning, you'll observe that in meta learning the the underlying low dimensional structure is not as apparent, and which is why like I would argue that strainer has a better ability to represent common structures across different signals. Of course it depends on the signals you pre-train on, but definitely it has a better way to it has a potentially better way to represent that. There's one more question, which is regarding MetaSeg. At test time, how many iterations do you run to get predictions? Okay, this is a great question. Let me go back to that slide. Okay.
Kushal, could you also repeat the question when you
Yes.
answer?
So the
Yeah.
question is regarding MetaSeg. At test time, how many iterations do you run to get predictions? And do the encoder features get fine-tuned too? That's a great question. So at test time, we fit it for t equal to 100 steps. Now, t equal to 100 steps is something which is a hyperparameter, and we fix it to t equal to 100, and I will explain where the 100 comes from. Now, when at test time, you only fit these MRI signals, so the gradient is flowing back to the signal reconstruction head and this initial shared encoder, but the segmentation head is frozen. So that answers the first part of your question. And yes, the encoder features will get fine-tuned, so that's correct. And then t equal to 100 comes from this previous slide. So once you learn the meta-learned initialization, you want to fine-tune your segmentation head, right? Because an initialization is not equal to a trained model. An initialization only initializes, right? So for the INR part out here, the initialization is good because you're eventually going to fit the signal. But for the segmentation head, you need to basically treat it like a classifier. So what you do is you create a data set of these per pixel INR features from your training data, right? So for each training signal, you send a coordinate as an input, you extract this feature vector, and you create this data set of those feature vectors. And then you train the segmentation head on oops, sorry you train the segmentation head to minimize a classification loss essentially. And you compare it with this one hot coded ground truth labels from a segmentation map. So that's where, so the t equal to 100 actually comes from this step where to get this data set of per pixel INR features, you render your INR for 100 steps. So essentially, you're fitting your signal for 100 steps first, after which you extract the features from your encoder. This is still during training time, by the way. And then you fit your segmentation head. All right. Next question is, from your perspective, do you think INRs can be implemented in harmonization across MRI data in different MRI scanners? That's a great question. Um, I would say that the initialization in an INR has a lot of value whenever it comes to generalization. So if your goal is to just use an INR to basically fit MRI signals from different MRI scanners, maybe how the initialization is structured plays a bigger role in that. Okay, so the next question is, every time the INR based network segments an image, it needs test time conversion. is more epochs for test time optimization better results, and this MetaSeg has less parameters, but will okay. So this question is basically about um, as the number of iterations proceed more, while an INR converges, would that imply better segmentation? And is is more number of epochs for a test time optimization better for better results? Okay, it's a two-part question. And the third part of the question is MetaSeg has less parameters, but the inference time will increase. And do you think Gaussian splatting training loss would be beneficial for continuity with an additional SSIM loss? Okay, this is a great question. So yes, the number of iterations you need for the optimal result is something you can decide as the hyperparameter. So out here we decide t equal to 100. Uh, and what you notice is eventually, and this is something we show in the paper, like it's a figure in the paper, eventually, if you fit until like t equal to 2000 steps, you will notice that because your INR is only fitting the signal, the segmentation quality will eventually deteriorate. So it so basically your segmentation quality follows almost like a Gaussian sort of curve where it is going to have the best quality around t equal to 100. That being said, that yes, MetaSeg has fewer parameters, and your observation is very right. So yes, MetaSeg has 90% fewer parameters, but because INRs are iterative, the number of flops or floating point operations done on your GPU may be the same, or maybe it might even be higher than like a highly efficient CNN. And do you think Gaussian splatting training loss might be beneficial? I haven't worked with Gaussian splatting, so I'm not sure about that, but maybe it is.
Mm.
Okay, there's a follow-up question. Does the size of the INR model matter significantly? Oh, that's a fantastic question. So INRs are good in a very unique way where you need a bigger INR if your signal is more complex, right? Of course having more parameters and over parameterizing a model is great in terms of the quality of fitting you can get, but there's a lot of work done exploring the different kind of INR architectures, different kind of ways to encode coordinates. For example, like Instant NGP proposes a very different way to encode coordinates, right? And they use a very small INR instead. And there are other works which use different activations or larger INRs. So there's a lot of interesting literature in this area, but I think my short answer is it really depends on the complexity of your data.
Right. I have a
Yes.
follow-up question on
Mhm.
that. So, regarding the encoding of the different coordinates, what are encoding schemes did you use in your methods? And uh, did you compare different encoding schemes like
Yes.
Unfiddle, STFs, uh, and what did you
Yeah.
end up using?
So So for both Strainer and MetaSeg, we actually didn't do a rigorous evaluation of different encoding schemes. Uh, we use the Siren model uh, as our like base model for everything, and the way Siren does it is because it has sinusoidal activations, you end up getting the same effect as like how someone doing a Fourier encoding like would get. So we
Right.
didn't really look into that as much.
And I was also wondering that in your first paper, you showed its generalization capabilities, that it was trained on one data set and it was able to generalize on the other data set.
Mhm.
Did you do any experiments for your MetaSeg paper? Train on one data set and see its generalizability on another thing?
Yeah, so I think back for MICCAI, like we were on a time crunch, so we didn't really
Yeah.
evaluate that. So yeah, but that's a very interesting question to
Right.
like look into.
Right.
And
And
then
I was just curious, what other interesting directions are you now pursuing uh, with INRs?
yeah, I think with INRs in general, so one of the things I'm recently very invested into is making Alpine, and the reason is that I think it's a good blend of research and engineering at the same time on how to write performant, like scalable code. But I think in terms of INRs, I like the signal of large signals. The area of large signals I think is very interesting from a machine learning point of view, where a lot of models that we currently have would scale terribly. if the signal size was humongous, right?
Mm.
And I think one very basic example is histopathology, right? Histopathology or microscopy slides are generally gigapixels. And then like a very naive way to use them in machine learning would be you basically either resize them to a smaller resolution or you crop, right? And the moment you do either of those operations, you lose a lot of details, right? But like maybe a good way to look at this from an INR point of view is you can encode a larger signal in a much shorter way, in a much shorter data representation, and maybe that has some more value.
Mm.
So
Yeah,
yeah.
I think yeah, you can continue
Oh,
answering
I
that.
can I can
Yeah.
finish off the remaining
Yeah.
Q&A. Are there special considerations while designing initial layers of INR and its parameters? Um, so, like for example, if you use a siren INR, each layer has this parameter omega, which generally there are like pretty standard values on how you want to initialize omega. But maybe sometimes if your task or your data is extremely unique, you might have to play around with that parameter. But other than that, no special considerations. There's a question: can we use this for something like histopathology? What concerns me, unlike MRI, those pictures are not in standard coordinates. So INRs don't necessarily need standard coordinates. You can easily use them. You could potentially use them with a non-standard coordinate system as well. So might as well try it. And then the last question is for figure 5 in MetaSeg. It's showing that the PCA of the penultimate features for an INR that is fine-tuned on a new signal at test time. Yes, it shows the PCA of the penultimate features at test time. If so, what does it look if you just query the reconstruction immediate after meta training? So immediately after meta training, if I remember correctly, you do see semantic features being embedded, but they will emerge the most once you fit a signal. So generally, I let the INR fit to a signal for the features to get very strong. But for example, out here in Siren, even if you fit the signal, you still end up with very seemingly like random components because Siren only fits to intensity, but Metaseg is fitting to intensity and semantics both at the same time. So you get a more pronounced effect when you let the INR fit the signal. Okay, that is all the questions.
Yeah, those were a lot of questions. Thanks for answering.
Yes.
Um, I think there's one more
Oh.
which just popped up.
Which
Yeah.
just popped up. Will the coordinate of images be important for results? For example, in OSS, images are centered, but the brain is not centered. Will it be optimized? Okay, this is a great question. Um, So OSS MRI is a fairly homogeneous data set, and it does help a lot where images are centered. So in our paper in the discussion section, we also mentioned that if your images are unaligned, which means you may have a translation shift or rotation shift, which is common in MRI images, you do get a drop in performance by some percentage. I don't recall the exact numerical value, but in it's we mentioned that ablation in the discussion section of our paper. Okay.
Uh, well, that's a great discussion so far. Uh, I have one more question,
Mhm.
since we still have time. So correct me if I'm wrong. So at the end of the day, your approach gives good initial features which can quote unquote be fine-tuned for a downstream task. Like potentially it could be used if you just freeze the metaseg INR, right?
Mm.
And again, since you draw inspiration from meta learning, which again is another way of achieving domain generalization. Um, so I was wondering, have you compared your work with other meta learning based approaches by just taking image and predicting the segmentation? How well that performs compared to an INR based meta learning approach? Uh,
Oh, so if I understood your question correctly, are you referring to like the other meta learning works in like CNNs or like transformers, things like that?
Yeah, meta learning based segmentation methods.
Yeah,
There are a few MICCAI papers as well.
yeah. Hmm.
I think couple of years ago, where they have like source domain and training domains, like meta train domain, meta test domain, and then
Yeah,
they
yeah.
learn a generalizable feature representation. But what I'm saying is that they don't use INR, they just do segmentation, images and segmentations.
Hmm.
So I was wondering, have you looked at how INR based meta learning
Yeah.
compares with that?
Not really, at least for this paper. But that
Mm.
that seems like a very interesting direction to even to like check how meta learning as a paradigm works differently across like CNNs or INRs. I think here, since we were just introducing uh, this as a new approach, we
Yeah.
really we didn't have the time back then to even like compare with other meta learned CNN methods. But also, I feel like CNNs and UNets in general have been like so optimized for the task of segmentation
Mm.
that I would not be surprised if they currently they outperform like MetaSeg.
Yeah.
Yeah.
Yeah. Okay.
All right. That's great.
Well, there's one last question maybe we can take,
Oh,
which is again in the chat, in the Q&A.
have you thought about how to make the model translation and rotation invariant? That's an interesting question. Uh, no, I haven't. And mainly in both with strainer and MetaSeg, we observe that like these features they somewhat are very highly tied to the orientation of your signal, and which is why it actually helps that in strainer and MetaSeg both the signals are well aligned. So yeah, I guess yeah, that's a good interesting question.
I think maybe group equivalent networks might be
Hmm.
helpful for getting this invariance and equivariance.
Oh,
Uh,
interesting.
maybe uh,
Yeah.
try to use that as like try to use those as layers and see if you get any
Hmm.
that could be in potential comparison or just a follow-up.
Oh, nice.
Great.
Okay, I
Well,
think that's all the questions.
that's a great discussion. Well, thanks again, Kushal, for uh, talking on a Saturday, and thanks everyone again for joining us and asking amazing questions.
That's
Uh,
great,
yeah,
and
we
thanks
will
for
post.
having me here, and thank you for everyone who posted these questions. And these are really, really interesting questions.
Yeah, and the recording will be out in a couple of days in case someone wants to review and ask him more questions. Yeah.
All right.
Thanks, everyone. Yeah,
Bye bye.
bye.